In order to explain some of the unique features that are available in Haskell, we need to understand how how Haskell programs are executed. In other words, how computation progresses in Haskell. In general, in functional programming languages like Haskell, computation is a mechanical process of rewriting definitions. So we have definitions which allow us to replace expressions on the left hand side by expressions on the right hand side. And the process of computation is just to keep on doing this until no further reduction is possible. So this process of replacing left hand side by right hand side is often also called reduction. So when no further reduction is possible, we have potentially an answer. Now, of course, if this expression is of the type that we want, if it's an int or a bool or something, then it is a valid answer. If it is of a form which is not in the type that we like, then we will get an error saying that some definition is missing. To start with, Haskell has built-in definitions for the built-in types. So when we have an arithmetic expression like 3.5, then Haskell knows that it can be simplified to 8. It's not important for us how these definitions are built into Haskell, but these are obvious things that we all know, and this is what it means to say that these are available to us to start with. So similarly, Boolean expressions like true or false would be rewritten as true. Now, in addition, obviously, we provide new definitions through our Haskell function definitions or our Haskell programs. So here is a definition of the exponentiation function. So it says that anything raised to the power 0 is 1. So this is the base case. This says x to the power 0 is always 1. And then it says x to the power n, if it is not 0, is going to be x times x to the power n minus 1. So this is just a basic inductive definition of the exponentiation function. Now, suppose Haskell is confronted with an expression of the form power 3 2. That is, we are supposed to compute 3 to the power 2. So at this stage, the only thing that can be simplified is the definition of power itself. So using the function that we have defined, we get the definition that power xn is x times power x to the n minus 1. Right? So now this n minus 1, 2 minus 1 is now an arithmetic expression that can be internally simplified. So using the built-in simplification, we replace 2 minus 1 by 1. So we get 3 times power 3, 1. Now once again, we can't evaluate this multiplication because the right hand side is not yet a value that can be multiplied by 3. So we have to again appeal to the definition of power and expand power 3, 1 as 3 times power 3, 1 minus 1. Right? This is just a blind substitution. This is what you should remember. It just says that power xn should be replaced by x times power n minus 1, x n minus 1, right? So this is just a plain substitution. It doesn't require any intelligence on the part of the system. It just says if I see a pattern which looks like this, I can replace it with a pattern that looks like this, where the corresponding values will be transported to the corresponding places. Okay? So now again 1 minus 1 is a built-in expression, so we can make it 0. Now fortunately power 3, 0 has a simple form which is 1. So using the user definition for power 3, 0, I get to 1. And now I can start applying arithmetic internally. So I get 3 times 1 is 3. So I get 3 into 3. And then 3 into 3 is 9. And so by this process of simplifying using a combination of the definition of power which we provide and the arithmetic expressions for subtraction and multiplication which are built into Haskell, we reach the conclusion that 3 squared is 9. Right? This is not because Haskell knows arithmetic or it knows anything about exponentiation. It's just that the way we have defined the computation rules, it ensures that the answer is meaningful. Now there may be situations where more than one thing is possible. In our previous example, at every stage more or less we could do only one thing. Maybe at this point we could do two things where we could multiply 3 with the bracketing we can only do one thing. We do 3 times 1 and then 3, but we didn't have brackets. We could possibly do this in different orders, but there will be situations where it is ambiguous. So here for instance we have an arithmetic expression which has two sub expressions which need to be evaluated. So I have 8 plus 3 times 5 minus 3. So if I choose to go left to right, then I first replace 8 plus 3 by 11 and then replace 5 minus 3 by 2 And finally, we have something where we can multiply and get 22. But we could, of course, just as well do it the other way. We could start with 5 minus 3 and make it 2, and then move to 8 plus 3 and make it 11, and still we get the same answer. So we are familiar with the fact in arithmetic that this will not matter. It doesn't matter whether we simplify 8 plus 3 first or 5 minus 3 first. So either order will reach the same result. Now, the same could happen when we invoke a function like power. For instance, supposing we invoke power with the arguments 5 plus 2 and 4 minus 4. Then if we choose to start with 5 plus 2, then this becomes power of 7 4 minus 4. Then I replace 4 minus 4 by 0, and then the power definition for 0 gives me 1. But if we do it the other way, something interesting happens. So now we start with 4 minus 4 and replace it by 0. Okay? And at this stage now there are actually two definitions that we can use, because the definition of power for 0 says power x 0 is 1. In other words, we could just as well have written power underscore 0 is 1, because the x plays no role here. See, the x is not used. Right? So we said at the beginning that if we have a pattern in which the variable that we are matching is not used in the answer, we can as well make it an underscore. So even though we have said x, the value of x is not used. So in particular here, Haskell can look at the definition of power and that the second argument is 0 and just ignore this argument and give 1. Right? So we have evaluated power in two ways, but the second way we have done something which is somewhat unexpected, which is that we have reached the final answer while not evaluating something in between. So this is perhaps a curiosity, but what if we did something like this? So we know now that power anything 0 evaluates to 1 without looking at that anything. So what if we replace that anything, okay, by a division by 0? So logically, if I write div3 0, then I should get an error. But if I say power div3 0 0, would Haskell expose that error, or would it blindly apply the definition for power anything to 0 and give me a 1? So we will come back to this very shortly in the same lecture. So Haskell therefore has to make a choice about what order to evaluate expressions. So we have seen that Haskell expressions are of the form f applied to e. So we call f the outermost function and e the expression to which it is applied. E in turn could of course contain more functions and so on, but they are inside. Okay, so here is an example. So we have an expression which says take the head of the list 2 appended to reverse of 1 to 5. So there is an inner function reverse, okay, and then there is an inner operator colon, but the outer function in this is head. So in our terminology, if we say f of e, this is head of something. So that something is e and f is head. Now what Haskell does is it prefers to use a definition which applies to f rather than definitions apply inside e. So in particular here, if I have a choice between expanding reverse 1 to 5 and taking head of the list, then I would first try to use the expansion for head. Right? So Haskell goes outermost. It tries to use the outermost definition that it can use in the current expression to reduce. So in this case, it turns out, for example, that you can take head of this list. Now head of x colon x's gives me x, right? We know this. So this is a kind of built-in rule in Haskell. So in this expression, the head value is known, it is 2. So without evaluating reverse, you can extract the head. Right? So this is what Haskell would do. It will try to get the answer with as little work as possible, if you would like to think of it that way, and hence this is sometimes called lazy evaluation. So the argument to a function in Haskell is not evaluated if the definition of the function doesn't force it to be evaluated. So I have no interest in knowing what the result of reverse 1 to 5 is, because it's not going to be part of my answer. So head of 2 colon reverse 1 to 5 just gives me 2. On the other hand, if I want the last value of the list, then I do need to know what happens to the end. So if I say last of 2 colon reverse 1 to 5, then I must reverse this list and get 5, 4, 3, 2, 1, so that I can then conclude that last of that definition of that list is 1. Right? So Haskell's lazy reduction starts from the outermost thing, and if it finds it has enough information to process the answer, it doesn't need to look at an argument, it will just ignore that argument. So if we come back to the question about what happens to power when we give it a nonsensical argument in the first position but 0 in the second position. So Haskell's uh, strategy would be to first look for a matching definition for power. So it finds a matching definition of power. This matching definition does not require me to evaluate x, so it ignores x. So this would actually give me 1. So let's see how this works. So just to convince you that this is real, so here is a Haskell file which contains that exact same definition of power. It says power of x0 is 1, power of xn is x times power of x n minus 1. So now if I run this, I say power, say for example 3, 2 as we had seen before, or power 7, 5, it works correctly. Now if I say power div 3 0 to the power 0, I get 1. And this is not because div 3 0 is a sensible expression, it's because div 3 0 on its own gives me, as I would expect, a divide by 0 error. Right? So lazy rewriting allows me to compute some values even though the arguments are not fully defined. Fortunately, in general, this order of evaluation, even in a functional expression, does not matter, just as it does for arithmetic, it does not matter. If all the simplifications are possible, whichever order we choose, then the order does not matter. We get the same answer. But as we have seen, if we choose one order, for example, in this our power example, if I choose the order in which I try to evaluate the argument before the function, then I will reach a situation where the computation doesn't terminate or it terminates with an error. Whereas if I use the outermost things, it does terminate with sensible answer. Now, this is not to say, I mean, we are not claiming that arithmetically something like infinity to the power 0 should be 1. Okay? So it's just saying that as per our rules, it is possible to conclude from this expression that the answer is 1. It doesn't mean that it is arithmetically a sensible answer. So the point is that using outermost reduction in this case, you get some expression which terminates, whereas if you use innermost reduction, that is you start from the arguments and move outwards, then you will get a situation where your computation either doesn't terminate or gives an error. So lazy evaluation is also called call by need. Okay, it uses the arguments only if they are needed, and therefore, as we have seen, it can terminate even though there are undefined sub-expressions which are not used in the computation. So why is this useful other than curiosities like power? Well, let's look at this definition. Okay? So here is a definition which creates an infinite list. So infinite list, it says, okay, is of type list of int, and how you get it is by calling an auxiliary function with an argument 0. And what does this function do? If it takes an n, it sticks it in front and then calls itself with n plus 1. So if I call inf list augs with 0, this becomes 0 and then inf list augs 1, which in turn becomes 0, 1 and inf list augs 2, okay, and so on. So in other words, this is going to, the 0 will produce a 1, the 1 will produce a 2, and so on. So this is going to produce an infinite list starting with 0. So we can verify that. So here we have again the definition that we just wrote. So we have inf list .hs. So if I put this into GHCI and I ask for what infinite list returns, indeed it does return an infinite list. That is, it just keeps going. So Haskell is able to somehow generate this infinite list and show it to us because it generates it one at a time. So as we have seen, infinite list, the definition given above, produces this infinite list. Okay? And if we just run it in the interpreter and ask for the value of infinite list, we just get an unending stream of numbers. On the other hand, if we ask for some function on this list which does not use the entire stream, then we can get a sensible answer. For instance, if we ask for the head of this list, then as we saw before, what Haskell will do, it will try to apply a definition for head. But head will ask that I need some values in the list in order to compute the head. So then I will expand infinite list just enough. So infinite list will now be expanded as inflist augs 0, which will in turn become 0 colon inflist augs 1. And at this point we have a value, so head of will come out as 0. We could also have a function which requires more of the infinite list. For instance, suppose we wanted first two elements. We say take 2 of this infinite list. Then in order to get anywhere, we first have to get the first element, and then we take it out, and then we have to recursively take 1 of the remaining. So again, we have to get this 1 value out. And then once we have got 2 values out, then we can stop and say that take 2 of this list is 0, 1. So in other words, by using lazy evaluation, we can take infinite lists and productively use them in our code. So in fact, Haskell allows us to define infinite lists directly using the range notation. If you remember, we had this notation from n to n, the list from n to n. So now if we leave out the upper end, then we get a list which doesn't have a terminating point. So m dot dot is just m plus 1 and so on. We can also write an infinite list with some arithmetic progression like things, so m plus d, m plus 2d and so on. So you might ask why this is useful. Well, it will turn out we will see later examples where allowing infinite lists in the definition of a function makes it simpler to argue about it, because if we don't know in advance what is the upper bound of the numbers we are looking for, then we can just provide an infinite list and let Haskell figure out how many of these numbers it needs. Okay, so to summarize, the process of computation in a functional programming language is rewriting or reduction, and this applies rules from left to right to reduce expressions using the definitions which are either built into the language or provided by the user. Now this allows multiple orders of reduction. Different expressions in the same, different sub-expressions in the same expression may be available for reduction. So Haskell uses what is called lazy evaluation. It simplifies the outermost expression first. And one of the consequences of lazy evaluation is that we can now work with infinite lists in Haskell.